on the first one, some of you used polar coordinates, and since it was from section 1, which was before polar coordinates, the idea was to use Cartesian there. So, any questions on homework that you might have right now?
Web work number 2.
Web work number 2. Okay. Okay, let me switch over here so I can write. All right, finally. I'll try to sketch this for you, but the idea is you have this horizontal cylinder, x squared plus z squared equals 9. That's a cylinder of radius 3 that's going along the y-axis. And then you have this other cylinder of radius 3 that's going along the z-axis. And the vertical one intersects the horizontal one, and the idea is to find the area of those patches that are extracted, in a sense, from that horizontal cylinder. So let me abuse my writing abilities here, and then coming up through the middle. Is this other cylinder. And so this patch, it's like that. And going in here is the y-axis, and going through here is the z-axis. And the x-axis, I guess, is coming out of the board at us. And in fact, I guess those guys probably come down and touch. If I were really being careful here, something like that, it would be even more accurate. Okay, but now it looks messy. Anyway, so does everybody kind of have that in their heads? Chris, yes? That was what you had in your head? Okay. Now, remember when you're doing surface area only works when you can solve for z as a function of x and y. There's no way that you can describe this surface, which has a top part and a bottom part, as a single z equals f of xy, because it fails the vertical line test. So what you have to do is back off a little bit. You've just got to find, say, the surface area due to the top, and then multiply that by 2. Is that the approach that you took?
That's what I was thinking. I guess I just said that.
And so once you recognize that you have to have z equals f of xy, let's solve for that. That's f of xy. And you might think that's a little weird because there's no y in there, but that's what it is. And that's the top. So
Should it be 9 mass x squared?
yes, sorry. So that's the top patch. Now what do you have to do? Okay, well, yeah, you've got to go through that whole thing. You've got to find fx, fy, which is 0. I can do that one. Fx, and then you've got to build this guy, fx squared plus fy squared plus 1. And you shove that into an integral and integrate it with respect to dx dy. What's left before I can finish this? I've got to find the region. The region is the area in the xy plane above which the surface exists. What is that region? It's a circle of radius 3. So you've got this vertical cylinder that's cutting this horizontal cylinder, And that vertical cylinder has a cross section, x squared plus y squared equals 9. So this region, do I dare? Let me, that region is kind of right in here in the xy plane. So I don't know if this was susceptible to polar or not. Anybody that did this one? It was an okay polar one. Anyway, if it's polar, then it would go 0 to 3 and 0 to 2 pi, and then you would integrate the polar version of this, and then r d theta, and then when you're all said and done, that's the area of the top half. So you multiply by 2. Okay. Andy.
What's the Cartesian version of the limits of integration?
The Cartesian version of the limits of integration would be, minus the square root of 9 minus x squared, say, to plus 9 minus x squared, and then you could go from minus 3 to 3, and then whatever, and then dy dx. That would work.
Okay, so the function that you're putting into the f of, or the partial of x squared is the same as the limits of integration for dy. Okay, I think that's just where I got confused, because I didn't understand what the was supposed to be.
Well, the difference is that these limits in this whole scenario are living in the xy plane, and this guy is living in three-dimensional space, and so it's this horizontal cylinder thingamabob.
All right.
Okay. Other questions? Sir.
What were the one with the cone? I think it was the 5.
Okay. What's the question?
I was having trouble setting it up.
All right, so we've got a sphere of radius 2, and then we've got this possibly peculiar notation. You know, whenever you're faced with an inequality like that, it's always going to be instructive, if you're a little bit confused about what's going on, it's always going to be instructive to change that to an equality and see what it looks like. So if I change that to an equality, what kind of surface does that represent? Yeah, it says cone, right? There are lots of different cones, right? There's really broad, flat cones, and there's tall and skinny cones, right, that all come down to a point. What can you tell me about this cone to help me really narrow it down and you know, get a grip on what this cone actually looks like? It goes up at a 45-degree angle. That's exactly right. So how can you see that? Well, if z is equal to the square root of x squared plus y squared, in polar coordinates it's just equal to r, which means that the height that the surface is above the xy plane is precisely equal to its distance from the z-axis. And that gives you essentially an isosceles triangle, or even better, you know, this 45-degree triangle. Okay, did everybody buy that? Now, what does it mean when you throw in that inequality? So we understand what this thing looks like when it's equal. It's the surface of this cone. When I say it's greater than, what am I talking about? The space that's above the cone. And that's a lot of space, right? This cone goes off to infinity. I mean, it's unbounded. It keeps going and going, and it's all the space above that cone. That's what z greater than square root of x squared plus y squared means. Okay, so let's do a sketch here. And let's just sketch that in like that. Okay, so there is there's the cone, and I'm just drawing the edge of the cone, but you know, it's all the space inside of it. And then let's sketch in a circle. And we're talking about the surface area of the piece of the sphere that's inside the cone. Does that make sense? Okay. It's that surface area. What's the equation? Z equals f of xy of that patch. What's the equation of that patch? What's the equation of the sphere? Anna?
The radical of whatever radius is squared minus x squared plus y squared.
Yeah, so you have the full equation of the sphere. And I don't remember either. 2. And so I can solve for z, at least the upper part, like that.
Radius to us is 4, right?
Oh yeah, good point. Thank you. All right. What do I do with this? Yeah, so this is f. That's f of xy. I'm being redundant now, but whatever. Fx, fy, and plug that into the square root thing. Okay. So that's going to get me the integrand. Now what do I have to do?
Find the region.
I need the region of integration. So where in the xy plane does this surface live?
X squared plus y squared. Plus root of x squared plus y squared plus 2.
How would you figure that out? Okay.
The circle where the cone just actually straight.
Exactly. So it's the projection of where the cone intersects with the sphere down onto the xy plane. How do you find that?
45.
Let's pretend that you didn't have such a great visualization. Well, you didn't have such an adequate visualization. How would you do it algebraically?
So you could plug z into z equation for the cone to the z where in the sphere.
So we've got z equals, we've got this part, right? And we've got this part. We can set those guys equal and get something like that. Square both sides. Move the x's and the y's to the left. Divide out the 2. And that is the equation of that circle. So it's a circle of radius root 2. So now let's build the integral. I'll do it in Cartesian, and again, this may be better polar. I don't know, for those of you that have done it. Polar was pretty good. So if you want to go polar, uh, 0 to root 2, 0 to 2 pi, the polar version of this, r d theta. Okay? Okay. Other questions? Okay, that's good. Today, triple integrals. And I promise that we're stopping at triple. So we did 1, then we did 2, now we're doing 3, we're not doing 4. Doesn't mean there aren't quadruple integrals. We just stopped calling them that after 3.
What they call it.
Then they're just called integrals. And you figure out how many integrals there are from context. That said, I can't think of any of you that would encounter more than 3 integrals unless you went to graduate school in mathematics. Okay? So you're safe from multiple integrals past 3 unless you go to graduate school in math. I will be fairly brief about this subject and then mostly do examples because this is all just sort of a natural extension of stuff that you're already doing. So the idea here is to think about adding another infinitesimal to the area element. So triple integrals sum up infinitesimal volumes. And so we're going to generically call an infinitesimal volume just dV. And you're going to see today that dV is just dx times dy times dz in any particular order that you want. And if you think about it, that's just a tiny little cube. Dx, dy, dz. It's just a tiny little cube that then the integral sums up all of these guys. But on Friday, we're going to talk about triple integrals in cylindrical coordinates and spherical coordinates, and then this guy becomes something different, something altogether different, in much the same way that the polar coordinate dA is different from the Cartesian coordinate dA. Nick?
That'll give you like little discs, right?
Yeah, so in polar, and I don't want to dwell on this too much, but in polar you can remember that everything was sort of shaped like everything was sort of shaped like a sector from above, and then you just sort of fatten it up to give it some volume. And then that was cylindrical. In spherical, it's even a little crazier, and we'll talk about that on Friday. Okay, so once you accept that we can sum up little pieces of volume using this notation, then you can get the volume of a region in 3D space, the volume of some region, oh come on, there we go. The volume of some region E is the triple integral over E of 1 dV. And there's nothing earth-shattering going on here. In fact, you would probably never really want to compute volume this way. You'd probably just rather go back to double integral and compute volume that way. But this is where we're going to start today, and then we're going to end up integrating other things, integrating things that are not 1 and interpreting those appropriately. But here's where we're going to start. We're going to start by computing the volumes of various shapes using triple integrals. The way that this is going to work, we're going to start with dV equal to dz, dy, dx, just because I think it's the most natural way to think about these problems. But you should know that the integral, just like the double integral where you can reverse the order of integration, with the triple integral you can reverse the order of integration, or better, I would say you can shuffle the order of integration to any order that you like and still get the same result. In two-dimensional integrals or double integrals, how many different integrals were there? There were 2, right? In 3 dimensions, how many different ways can we shuffle? 6. right? 3 factorial. So, and 4 dimensions, it just gets greater and greater, right? So in 4 dimensions, it's 4 factorial. In 5 dimensions, it's 5 factorial. So there are a lot of different options here for dv. We're going to start with dz, dy, dx, again, because I think it's the most natural way to think about it at the start. Okay, so as I have a tendency to do, let's start with an example where we already know the answer. So let's compute the volume of a sphere of radius A. The way this is going to work is you work from the inside out. So we've decided to go dz, dy, dx. So what I want to do is I want to first ask myself, where is z trapped? Where's the lower limit of z and where's the upper limit of z when you're inside of a sphere? Well, you can go from the bottom hemisphere to the top hemisphere. And those are described by equations. So we've got x squared plus y squared plus z squared equals a squared. And if you solve for z, you get plus or minus square root a squared minus x squared minus y squared. We've done this 100 times. The plus or minus now actually are important. The plus is the upper hemisphere, the minus is the lower hemisphere. So z, no matter what else it does, z is trapped between these two surfaces. So the limits of integration with respect to z are these. Okay, let's add the next layer. Once you've satisfied yourself with z and the limits of z, now you're back down to a double integral. So over what region in the xy plane is z trapped? Well, this is a sphere of radius a. So what does its intersection with the xy plane look like? Circle of radius a, right? What are the Cartesian limits for y for a circle of radius a? Well, that's x squared plus y squared equals a squared, right? And y is equal to plus or minus the square root of a squared minus x squared. So the lower limit is this negative the square root of a squared minus x squared, and the upper limit is positive the square root of a squared minus x squared. And the last variable, between what x values? Negative 8a. I know you've done this a lot, so we'll keep it quick. That's pretty messy. Let's stick with Cartesian for a little while here. I'm going to do, so the way that you do these integrals is very similar to the way that you do double integrals. You work from the inside out. So that first integral is actually not too bad, right? What's the integral of 1 with respect to z? It's just z, right? And then you plug in the limits and subtract, and so that integral just falls out to be right? At this point, if you want to go polar, by all means, go polar. Right? So this looks like a good candidate for polar. So that circle of radius A is very easily described in polar coordinates. R goes from 0 to A, theta goes from 0 to 2 pi. The thing underneath the square root becomes what? A squared minus r squared, exactly. Good. And dy dx becomes r dr d theta. We can do the theta integration right off the bat, and what's that get us? 2 pi. So we get a factor of 4 pi out front times the integral from 0 to a, square root of a squared minus r squared dr. How do you do that integral? Yeah. What would you let u be?
A squared minus R squared.
Yep. And du would be negative 2r dr. Let's make that substitution, 4 pi. I'll leave the limits for now. That's u to the 1/2. Oh, and there's an r in there, sorry. R dr is equal to negative 1/2 du. Right? The new limits of integration, when r is 0, what's u? A squared? And when r is a square, or when r is a, u is 0. Let me simplify that a little bit. That's 2 pi, 0 to a squared, u to the 1/2 du. Do you see what I did there? I switched the limits of integration, introduced a minus sign, and I combined the 4 and the 1/2. I think we're ready to do this integral. 2 pi, u to the 3/2 times 2/3 from 0 to a squared. That's going to be 4 pi over 3, and when I plug in a squared, I get a cubed, which is what we expect. Totally could have done this with a double integral, right? Does everybody see that? Yeah. I could have just integrated underneath. I could have just done the volume underneath the upper hemisphere and then multiplied by 2, and I'd be in the same place. In fact, I think I even did that as an example last week. So there's nothing really earth-shattering here. It's really this example. The purpose of this example is just to familiarize you with the process of thinking about z, then about y, then about x. Okay, let's do a slightly more interesting example. I want to do an example from the book, partly because the way the book explains it, I think, is a little opaque. And so I thought I would go through a slightly more detailed approach. So if we look at the book here, there's an example about a tetrahedron. A tetrahedron is a shape in 3 dimensions that's defined by 4 non-collinear points. So none of these guys, right, they're all on, they're not on, no 3 of these guys is on the same line. That's what I mean by non-collinear. And if you were to plot those 4 points, the vertices are here. 1, 2, 3, 4 vertices. So what I'd like to do is calculate the volume of this. Again, you could do this using a double integral, right? If you were going to do this with a double integral, what would you do? What's the first thing that you would do? Sure, you could find a formula for the plane. That would be the surface. Okay, what's the next thing you would do? Find the region of integration, which appears to be what kind of figure in the xy plane? Some kind of triangle. You'd have to sketch it out and make sure you figured it out. Once you have the surface above and the region below, then you can build this double integral, right? And you're perfectly capable of doing this using a double integral. But again, just for the sake of introduction, let's do this with a triple integral. But we still have to go through similar process. We have to find the equation of the plane. And the region below. if we find the equation of that plane above, then z is going to go from where to where?
0, Z.
It's going to go from 0 up to the equation, whatever that is. And then once I do that, then the rest of it is just describing this region in the xy plane. Let me write the points out on this page so that we have them. 0, 0, 0, 0, 3, 0, 2, 3, 0, and 2, 3, 5. Let's orient ourselves a little bit. The triangle in the xy plane is made up of which 3 points? The ones that have zeros in the z slot, right? All of those lie in the xy plane, and that makes the triangle. If we would like to build the plane, or describe the plane, how are we going to do this? Do we have enough information to define that plane? You need 3 points, right? So the real trick is to identify the 3 points that lie on the plane above the top plane. Which 3 points lie on that plane? 1, 2, and 4. How do you know, Ethan?
Because 3 and 4 are vertical in the Z direction.
Yeah, I guess that's as good as any, right? You don't want a vertical. You don't want a vertical. You don't want these 2 points to be vertical, right? So clearly, it's 1. What did we say? 1, 2, and 4. Yeah. So use 1, 2, and 4.
Would you be right if we just choose any 3 of them, or as long as you have 4?
You can't choose any 3, right? So let's talk about what happens if you choose other guys. Right? If I don't choose the right 3, then like if I chose these 3, then I'm going to get this plane. And if I chose these 3, this guy, and this guy, I get this other plane. So, or if I chose the 3 that are in the xy plane, then I get the one in the xy plane. So I've got to choose the right one. And it really is a matter of visualizing the figure and picking the right ones. Okay?
What would you do with the base, or if it was the whole thing was shifted,
Like only a point was on the xy
Yeah.
plane? Yeah. What you would do is change your coordinate system so that one of the faces was lying in the xy plane, right? Because there's no point in making your life difficult. So that's why this problem is presented the way it seems like, oh, wow, this problem is unnecessarily nice because 3 of the points are in the xy plane. But if you think about it, for a tetrahedron geometrically, I can always put 3 points in the plane. So I might as well just choose a coordinate system that makes that happen and make it easy on myself. And so that's what the author is doing here. So we've determined now that we can get the equation of the top plane by considering these 3 points. And you may or may not remember how to do that. You want to find 2 vectors that are parallel to the plane, take the cross product to get the normal vector to the plane, and then take one of the points that's on the plane and use that to build the equation of the plane. So we can get 2 displacement vectors that are parallel to this plane, for example, 2 minus 1 and 4 minus 1. So let's do that. We'll take the first displacement vector is going to be 2 minus 1, which is just 2. And the other one we'll call Q, and that's going to be 4 minus 1. And that's going to be just 2, 3, 5. Yep, okay. Build the normal vector. So that's the cross product. So what, 15 0, negative 6? Yeah. Build the equation of the plane. That's 15 times x, 0 times y, and 6 times z. So z is equal to 5 halves, I guess. 5 halves x. It just so happens here that z is a function solely of x. And that was just an accident of this particular plane. Okay, so the top plane is 5 halves x. Now let's look at the region. All right, the region of integration in the xy plane. Let's So which 3 points are in the xy plane? 1, 2, and 3, right?
Zero.
The one where z is 0. So we need to plot 0, 0, 0, 3, and 2, 3. What was it? 0, 0, 0, 3, and 2, 3. Why am I bothering to sketch this out?
It's limits.
I'm trying to find these limits in x and y, right? So I've got the limits in z. I'm trying to find the limits in x and y. Let's take a vertical slice here. At the bottom, what's y? Well, what's the equation of that line? 3 halves x. Good. So at the bottom, it's 3 halves x. At the top, what's y? 3. Mm-hmm. Okay, and we're almost there. X goes from where to where? 0 to 2. Okay, we're ready. The volume of this figure is a triple integral. Z goes from 0 up to 5 halves x. Y goes from 3 halves x up to 3. And x goes from 0 up to 2. If I asked you to do dz, dx, dy, could you do it? dz, dx, dy. Yeah, it would be fairly straightforward. I would just have to do horizontal cuts and make sure that x went from 0 out to 2/3 y. Okay, so you could do that. What would be significantly dicier would be to say, can you do dx, dy, dz? Right? Let's look at the figure here. So then, in the x direction, you would have to go from this plane here to this plane back here. And you'd have to find 2 equations of planes, and it would be pretty complicated. All right, so this is definitely the right direction to go, the right order of integration to use. I guess just for the heck of it, let's calculate this integral as well. The inner integral works out to what? Five halves x. Okay, the next integral. Works out to that. Why? Because it was a constant with respect to x. So I integrated this thing, this turned into a y, 3 minus that appears right there. And does everybody see that? And let's finish it off. Okay. This last guy. Oh, somebody's having fun over there. I'm just debating whether or not I actually want to do this. I think I'll let you guys finish it. So the last guy, you integrate with respect to x and plug in the limits 0 and 2. It's probably not that bad. So, okay. Any questions about this? All right, let's do slightly more interesting stuff now. So the real application of these, yeah, Lane.
Yeah, sorry, going back real fast. Am I right in thinking that we could check our answer by making a triangular prism with the base times the height and then dividing it in half?
Yeah, if you know that formula, absolutely. And again, these are sort of toy problems just to set up the process. So let's talk about some less toy problems. For example, the real value in these triple integrals is when you're computing, when the integrand is not 1. And there are a couple of examples from the section where the integrand is not 1. The first one is if you have a density function. So let's pretend you have a density function now not in some 2-dimensional piece of metal or something like that, but in 3-dimensional space. And for example, the density function in this room, it's really not very dense right here. Okay, but right here it's pretty dense. So the density of matter in this room depends on my location in the room, right? So if I want to compute, say, the mass of this region of space that has all this air and my head in it, then I have to know the density function for that region of space with all this air and my head in it. And then I have to integrate over that space density times dV. Density times dV gives you mass, right? It gives you the mass of a tiny little piece of volume. And you sum it all up, and you get the mass of this total of this volume. That's something that can't be reproduced, at least not easily and not generally, using a double integral. And that's why we have these triple integrals. And you can imagine what some of the applications are here. Finding mass, now you can find the center of mass of a 3-dimensional figure, which you'll have exercises like in here. Don't worry, x bar is just the triple integral of x times the density. Y bar is the triple integral of y times the density. Z bar, triple integral of z times the density, and then divide those numbers by the total mass. Right, so x bar, y bar, z bar. Now you've got 3 numbers, which makes sense because the center of mass is now going to be in 3-dimensional space. A lot more integrals, a lot more work, but it's doable. You've got some fairly straightforward examples for homework, nothing too onerous. And I guess let's look at some of the exercises. What I wanted to do now was, there are these fairly straightforward computational exercises at the end of the section, 1 through 7, pretty straightforward computation. I thought, especially if some of you are struggling with visualizing these things and struggling with how to set these things up, one thing that you might add to this would be to, and let me just put a note here, visualize the region of integration. You're not asked to do that in these problems. These problems are very straightforward. For example, number 2, you've got the limits, you've got the integrand. You would integrate with respect to z, plug these in, integrate with respect to y, plug these in, integrate with respect to x, plug those in. No thought whatsoever other than just basic integration skills. An interesting question is, why am I doing this? What region of space is this covering? So let's think about that a little bit. So let's focus on number 2 here. We're integrating dz, dy, dx. So that tells me that z is going from 1 to y. Interpret that for me. Great.
Would it be like a plane that's going along, kind of going up along the axis?
That's one of them. That's the upper limit. And the lower limit is the horizontal plane. So whatever else is going on in this region, you know that Z is trapped between a horizontal plane 1 and this other plane Z equals Y. Right? And Z equals Y isn't too terribly difficult to visualize, right? Imagine the YZ plane, right? The YZ plane. Z equals Y is that diagonal line. And then what does it look like? Just extend it forward and backward along the x-axis. So it's the slanted plane. And then where is Z equals 1? It's this horizontal guy. Now, we don't know, is Z over here between the plane and between the horizontal plane and this guy? Or is it over here between the plane and down here? Right? We don't really know where it is, but we do know that it's between those guys somewhere. That's all we know from the first set of limits. Let's look at the second set of limits. The second set corresponds to y. So that says y is equal to -1 up to y is equal to x squared. So now you're in the xy plane, and y equals -1 is just this horizontal line. And y equals x squared is this parabola. Okay, so we're narrowing things even further. So at first, from the first set of limits, we know that we're talking about space that's trapped between this plane and this plane. And now we shift our focus down here to the xy plane, and we know that we're trapped between -1 and this parabola. So we've almost got it bound. And the last step is 0 to 2. And that tells me that x can't go outside of 0 to 2. And the three together carve out a chunk of space. It's not super important that you completely visualize these things, but it is important that you kind of have an idea that you've got bounds in z, then bounds in y, then bounds in x. And they kind of carve out this space. And I think for most problems, just that generic spatial relationship is enough to get them done. How about 4? Let's do the same thing with 4. It's a little bit weird because it's polar cylindrical, so it's dz, dr, d theta. The first set of limits corresponds to dz. It says that z starts at 0 and ends up at r cosine theta. So z equals 0 is still just the xy plane. Now we're going up to r cosine theta. What does that mean? Yeah, that's just x. So if you're really thinking about polar coordinates, remember that the polar coordinate formula for x is r cosine theta. So this is really just z equals x. Okay, get out the xz plane. Here's z equals x. And it's the plane that comes out along the y-axis. So not too terribly different from what was going on right here. Does everybody see that? Okay, let's keep going. Now r is going to go from 0 to sine theta. Do you remember what that is? Sorry, not R, not Y, R. Do you remember what that describes? It's a circle. Do you know its center? A little tricky. 0, 1/2. 0, 1/2. I'll flesh it out for you, don't worry. So let's say that's 1/2. Okay, let's think about this. When theta is 0, what's r? 0. So that puts me right here. Now theta starts to increase, and it goes up to here. When theta is pi over 2, which is here, what's r? 1. That's right here. And then sine starts to decrease again until you get back to here. When do you get back here for the first time? At pi. So that circle is traced out over what range of theta? 0 to pi. Good. Okay, so we're kind of getting there. Let me draw in axes. X, I guess, and Y. Okay. So that plane, what was it, z equals x? That plane is sort of right here. Okay, let's keep going. So it's the space between the plane and the xy plane. All right, back to here. 0 to pi over 2. What's that tell me? Like the right half? Yeah. Okay, so now we have fully captured it. It goes from the xy plane up to this plane. And then it's inside this half of this circle. So I highly encourage you, even though the book doesn't tell you to do that, I highly encourage you to try to visualize some of these regions. I feel like if you can go in that direction, it might help you go in the other direction a little bit, which is a somewhat harder direction. All right, let's move on a little bit. Oops, I'm still drawing. Let's look at 10. Find the mass of a cube with edge length 2 and density equal to the square of the distance from one edge. My God, what are they talking about? Okay. A cube. Here's a cube, kind of. So now we've got this solid block of something, and it's a very peculiar kind of something because the density, say, is related to the distance from this edge right here. So if I'm really close to this edge, what's the density qualitatively? It's pretty light, right? Not much density. Does everybody see that? And it doesn't really matter, right? All I care about is the distance to this edge. So up here, right, it's light. Down here it's light, because all that really matters is not where I am vertically, but how far I am from that edge. Does everybody see that? So this thing gets denser as you head in that direction. Very weird cube. Okay. What I want to do is I want to position this cube in my coordinate system in a way that's strategic, that's going to make things easy for me. What would be a good place to put this cube? Hannah?
Of the edge that you're referencing.
This edge.
The z-axis.
Put this along the z-axis, absolutely. So I put that reference edge along the z-axis. Where's the origin? Maybe one of the corners. Yeah, I'll put it down here. Does everybody see that? Okay. So now I'm going to take that cube and I'm going to look at it from the top. And here, so coming out of the board at us is the reference edge. And that lower, so this is the top of the cube. And this is the XY plane. These distances are 2. And this is my reference edge. Does everybody see how it doesn't really matter which edge I choose? Right? It's a cube, so it just doesn't matter. So I'm choosing to take that reference edge, and the z-axis is coming out of the page. What's a formula for the density at the point x, y, z? Hannah.
X squared plus y squared.
X squared plus y squared. No z, right? All we care about is how far we are from that reference edge. Remember, the vertical doesn't matter. So the sigma, why isn't it the square root of x squared plus y squared? Yeah, because the problem specifically said that the density was equal to the square of the distance from one edge, the reference edge. Yeah? Good. Okay. What's the mass? What's the mass of a tiny little piece of cube? Let's call it dm. It's sigma of x, y, and z times dv. Right? What's the total mass of the cube? Well, I have to integrate that, right? I have to integrate x squared plus y squared dv. Cubes are really easy for limits of integration in Cartesian coordinates. It goes 0 to 2, 0 to 2, 0 to 2. X squared plus y squared dz dy dx. Does everybody see that? Okay. I'm going to finish with one last problem that's sort of more of a thought experiment than it is a math problem, but I like it. 14. Find the region E for which this triple integral is a maximum. This is a bizarre kind of problem, right? You're asked to maximize the integral not by, not by plugging in any particular numbers or what have you, but by choosing the region of integration. And I should tell you that generally speaking, there may not be an answer, but for this guy, there is an answer. For the sake of this thought experiment, pretend that the integrand is a density function. Pretend that it's a density function. What's the density of space near the origin or at the origin? 1? And what happens to that density as I creep away from the origin in any direction? It starts to drop, right? Okay. Well, if things start to drop and they start out positive, some point they have to hit 0, right? At what point does the density hit 0 here? Yeah, in fact, it hits 0 at a lot of points. Right? As soon as you're traveling away from the origin, and as soon as you get to that sphere of radius 1, every point on that sphere has what density? 0. Now we stop thinking about it as a density function. You go past the sphere of radius 1. What happens to that function? It goes negative, right? Which we don't understand as a density. It goes negative. Now back to the original question. What set E over what region of space should I integrate to make this integral a maximum? Sphere of radius 1 centered at the origin. Qualitatively, why is that the case? What's going to happen if I don't go all the way out to the sphere? I'm not getting all the positive stuff, right? And what's going to happen if I peek out of that sphere just one little bit in any particular direction? I'm going to start taking away stuff. There's going to be cancellation. So there's no mathematical way, at least not for you guys, there's no mathematical way for you to write this down and say, oh, E should be the sphere of radius 1. But it's a pretty clear thought experiment, right? I creep up, I creep E up, creep it up, I eat all that positive density until I get to that shell, and then I can't go any further past that or I'll start getting cancellation. Okay, you don't have, I don't think you have any problems like that. I think it's just worth thinking about this problem to help develop intuition. But you have problems about center of mass and density. So be prepared for that. I didn't talk a whole lot about center of mass because it just lifts right up from the two-dimensional case. That said, bring your questions on Friday if you get stuck.